funding, if that is correct. Yes, welcome on stage. It's great to have you here. And you have the clicker here for you.
Wonderful. Thank you for the introduction. Yes, Sophia and I both work at the DLR, but we work at the project management agency part of it, the DLR Projektträger. And as part of that job, we would like to talk to you about how we address the software gap. Because during our work there, we have to monitor the situation that's happening in quantum computing right now. And I don't know if you've had the same observation, but usually when you receive news about something that happened in quantum computing, it's one of two kinds. Either it's something like Amazon launches a new superconducting device somewhere, Google makes a great breakthrough in logical error qubits, the QCI unveils a new quantum computer somewhere. So somewhere we have a new breakthrough, great hardware somewhere, which is impressive results and great stuff. Or you receive news that something of this kind. Kipu Quantum and BASF team up to work on optimization. QEra does something with drug discovery, or we have an implementation for network performance somewhere. So we have a solution provider and an end user combining to tackle some use case, implementing a proof of concept in somewhere, something like this. But in between, we noticed a big gap, which we call the software gap, which is we have to bring these two things together because great computers are wonderful. Use cases are very, very important to actually produce value. But you need software to actually close the gap between the two, turn the algorithms into application, and actually integrate quantum computing into the classical infrastructures, into the existing processes, so that you can use your proof of concept use cases and the great hardware together to actually, at some point, create business value here.
Yeah, and now we think about how to address the software gap. And we did this through public funding. Actually, who's we? First of all, it's the Federal Ministry of Economic Affairs and Climate Action, which is supported by us, the DLR Projektträger, to have a really large project calling Development of Digital Technologies. It's not only about quantum software, it's also about AI and green tech, but there's also a lot of space for quantum software. And there we had at least two funding measures, starting with Planck, but we really had this nice talk in the morning today, so we actually learned something about that, which is really well implemented. And then we have a following call, concentrating on quantum applications for industry. And there we're looking especially at the development of platforms, tools, methods, and economic developments of quantum computing. And if you want to have more information about that, then you can just have a look at our website or just in this nice information sheet to learn more. But let's go into detail how we want to address this software gap by funding. First of all, you see on the right-hand side that we directly starting with the problems and then integrate it to the software, which is like running on different sets of hardware. So we actually do not fund hardware, but we fund the software and also the application side. So at least we have 4 major funding goals. First of all, the demonstration of use cases. At least we have 30 use cases in all of our 9 projects regarding optimization, simulation, and also quantum machine learning, starting from branches like production or logistics, or even chemistry or finance. The second point is that we are developing methods and tools for creating quantum solutions for real applications, so that we have at least here quantum software development or quantum engineering, or also decision trees to make decision whether your problem is better solved quantum or a classical way, so that we also have a hybrid approach within our projects. Third one is to simplify the access to quantum computers so that it's easier to get in contact with quantum. It's easier to describe your problem. Maybe that you have some platforms where you just mathematically describe your problem, but it's also easier to assess the hardware below, that you don't have to make directly a decision which hardware you want to use, but also there are some mechanisms helping you to find the right hardware for you. And last but not least, which is all bringing together, is build up the community of developers and users which are working together in these different fields. And with that, I hand over to Johann again.
Thank you very much. Now that we know what we try to aim for with our funding, we try to look at a little bit more at the software gap. How can we actually close it when we look at the quantum software stack? And if we look at the top layer, then it's the applications that is the goal in the end, and that our projects work on. So there's a lot of work putting POC use cases into actual services or actual applications. Of course, there's continued research on algorithms, further implementations, new developments of algorithms, but not just algorithms, but also implementing them in the next layer into libraries, patterns, workflows that make it easier for a software developer to actually make use of these algorithms. We also have a great project that you heard earlier about here in this very room that develops higher level programming languages because it's essential that we get away from implementing single gates to actually use all the knowledge from software engineering, classical software engineering that has been built up in the past decades. These programming languages then have to, or the things that are implemented in these programming languages then have to go down to the next layer to actually be transformed into the actual gates that are implemented on the quantum computer through compilers, through runtimes that decide which part will be performed on a quantum computer and which part on a classical computer, using assembly languages and the like. At the lowest level, before we reach the hardware, which is not part of our funding calls, is then the firmware that actually translates these gates into microwave signals and the like. And here we have a very, very messy overview of all the areas where our 9 projects contribute. So we see there's a lot of work on the higher levels of the stack, implementing applications, working on algorithms and libraries and the like. But we also have several projects that really work on developing software engineering tools and methods so that it's actually possible to close this software gap to actually implement the quantum computing solutions into classical infrastructures and processes. And because all of these names are just names, try and go on our webpage again to find out a bit more about these projects, what they're actually working on, what they have found out. Well, before we go to this cross-cutting topic of benchmarks, which you see here on the left, which spans the whole software stack, let me also quickly flash where you can also find out more about these projects here today and tomorrow. So you've already hopefully heard the great talk about CRISP earlier here in this room. There's also another talk about the case studies for optimization use cases from one of our projects later today. And tomorrow we have 3 more presentations from our projects about quantum machine learning automated for industrial applications, for user-friendly access to different hardware platforms, and then sort of in the late afternoon for using meta-solving strategies for quantum optimization. So circle these in your Bitkom event app, and hopefully you find out more about what our projects are doing. And with that, I hand over to Sophia again to talk about benchmarks.
So, as you already see on the software stack, benchmark is quite it's a topic which is like related to all, or like to the whole software stack. And so also all our projects are really interested in that. So why is benchmarking so important? As you could see here, 2 pictures which are generated by ChatGPT is how they imagine why it's important. On the right-hand side, you see just a comparison of algorithms. So there is a possibility to give orientation for the developers and users. Or in the second picture, you see the measurement of kind of a quantum computer. So at least you get all information about certifications and also characterization. And it's also important, especially in the NISQ era, where we need a high degree of precision for all the different components within the computer, so at least that we get some of the results. So that's why it was really easy that we started to determine within the project, cross-project, for application benchmarks. And within this, we'd like to address some of the following challenges which we observed. First of all, this is really hard to measure and evaluate performance and scaling of solution of real-world problems. Several benchmarks are concentrating really on this toy problem part, but we want to go a little bit more deeper and also address industry problems. Beside that, it's a lack of fair and simple standard set of benchmarks. They're missing baselines, they're missing a standard set, sometimes even explanations. Beside that, we also need resistance for realistic test instances for benchmarks, and we need access to different hardware, which is not so difficult, expensive, or time-consuming as it's already today. And last but not least, there's a lack of about the state of the art of the benchmarking. So a lot of people don't know exactly, especially in quantum, how to deal with benchmark or even in comparison to classical benchmarking frameworks. Therefore, we had 3 major projects. First of all, starting from the right is the development of the DIN spec, benchmarking quantum computers with determined KPIs. This is within the Enigma project, which is led by Fraunhofer Focus. You just can have a look at the QR kit and see the business plan. We're expecting the DIN spec by end of the year, so that we at least have some standard document, which is the starting point for a benchmark. Beside that, we're also working on a study on called WebMarkQ on web-based benchmarking services for gate-based quantum computers, which are actually building up a framework for benchmarks. This project was starting in July, and I think the first results are expected by the end of the year. Moreover, and this is a large part in the middle, we have also a cross-project study, which is already finished yesterday and also published yesterday. It's recommendations for action for public for application-oriented ideal benchmark. And this is more a mixture from political recommendations, but also recommendations if you have first starting point with benchmarks, that you just can get an overview, what are different types of benchmarks. We had a look at 34 different types of benchmarks, and the most relevant of them were evaluated by 7 criteria, which we have found out during our progress within our 9 project together with our 60 experts. And for each of the benchmarks, we also give you some calls for action, what to do, what are good steps to implement and to improve the benchmarks. Beside that, we also have this overall recommendations for action. And I just want to give you a really quick overview of what the most important points are for us. First of all, these benchmarks should be making real application the basic for benchmarks, so that we had at least here the application requirements considered, that it's also possible to go from one part or from one application towards another application, and that the benchmarks should not be so easy, so that it should be really applications that could face real world problems. Beside that, increased user friendliness is a really important point as well, meaning that we have explanations for different types of benchmarks, meaning that the people you have to use understand what they have to know, and that they sometimes don't have to know so much, but that there also be a possibility of testing, so that you, if you want to test, that you have a fail-pass test to get less resources for computing time, for example, and also computing power. The most important point, I think, for us is building up a benchmarking community. So we have at least to talk about benchmarks, coming up together to define kind of these baselines, to define real standards for benchmarking, not only in the different types of the software stack, but also below, also within the hardware. The next point is making benchmarks more independent. This is simply, for example, if you have a look at different types of platforms, that some benchmarks only work for one platform, but then you can simply, complementary benchmarks could be added to also understand and compare different types of platforms. Also, that you consider the special feature of hybrid computing. That means also have a look at what is important in the NISC area, especially, and also have a look not only on the quantum part, but also on the whole, also classical part, which is all around of the typical quantum computing phase. And last but not least, at least there have be different data sets for training and benchmarking, so that you don't have to have one data set which you're training, and then it's also the benchmark set for for the same benchmark. Then for sure you get nice results, but it's not even comparable to other ones. So this must be a really important point to consider that. So if you really want to have a look, and have a look also well to the other 39 or to the specific 34 benchmark types, then please feel free to read the paper.
And with that, I want to come back to the software gap, which I introduced in the beginning. So you've seen that we've already started filling in the first gaps of the software stack. You saw the software stack and how it's approached by the projects that we have funded in the past years. You saw how benchmarking plays a role in assessing how well we close that gap. So what's next? Well, we should build on these things, because what we have seen in these projects is we have made great developments, great progress, but it's individual tools that are results of these projects. But we haven't closed the full gap, but we have building blocks. So now we need to pool these results, bring them together, create an overarching framework that actually brings these things together. And with that, we have supported some funding from the BMWK, the Federal Ministry of Economic Affairs and Climate Action, to start a small project called QC Next, which explores the possibilities of such a holistic software stack framework. And they're currently in the phase of evaluating the different software stacks that are around. And they want to, of course, know more from the community. So they are hosting a workshop on November 6th here in Berlin. And I would like to invite the whole community to actually reflect on the software stack, their plans. And this would be very valuable to get the feedback from the community, because the results of this study will heavily factor into how we and the Federal Ministry will continue with our funding, what will be the next steps in public funding to close the software gap. So please sign up. And with that, I want to thank you very much for your attention. Bring up this last slide. We'll be here today and tomorrow if you have more questions. Join the projects that present their results here today and tomorrow. And of course, have a look at the results online and sign up for the workshop on November 6th. Thank you very much.
Sophia and Johann, thank you very much for your talk. We have time for one question. So whoever is first at the microphone gets to ask the question. Is there somebody at this point? I don't see a hand raised now. Last chance, else you just do the questions at the side, because Sophia and Johann, you will be with us the whole day, so just feel free to get in touch with them. And thank you again for being with us.
Thank you.